Welcome to today's lesson, 1.4, reading measurements. Today's learning target is I can read measurements from a graduated cylinder and a thermometer. This baby right here is a graduated cylinder. It's a cylindrical tube. It's used for measuring volume, which is how much space something takes up. And more often than not, we're going to be measuring in milliliters. Now, what does graduated mean? It just means that they put all of these measurements on it. They broke it up into smaller pieces. That's what graduated is. It does not mean that it graduated from high school. It means that we have little measurements all over it. And it's in the shape of a cylinder. Surprise. Next comes thermometers. Thermometers measure temperature. I'm sure you know this. I kind of even feel silly explaining it. But what's inside a thermometer? They used to be filled with mercury, but we've kind of learned that mercury is not so good for you. So we've moved more so to dyed alcohol, which is why they're red. Mercury is a silver liquid metal. So if you see one of those, I personally would get rid of it. And you have to go through a proper channel to get rid of it because mercury is toxic. Usually a county will have some type of chemical disposal to get rid of those things. You probably don't have one, though. Most people are working with digital thermometers nowadays. In your chemistry classroom, more likely than not, you're going to have a dyed alcohol thermometer. The reason they dye it is because alcohol is a clear color, which is very difficult to read inside one of these thermometers. So they dyed it red. What happens inside this thermometer is that when it's heated, this bulb has a pool of liquid in it, and when it's heated, all of the liquid in this tube is going to expand, and when it expands, it begins to climb up the tube, and then it will stop, and then you get your measurement. When your thermometer is measuring something colder than the air, the liquid in here is going to contract, or it squishes together, so all of this is going to fall down the tube, and it gives you a measurement then. Typically, our thermometers are measuring in Celsius, and then we need to convert it into Kelvin. Very rare to get a Kelvin thermometer. So these devices have very narrow tubes that allow for capillary action. This is essentially how water gets up to the tippy top of a tree. A tree doesn't have a heart to pump the water up to the tippy top the same way animals have hearts to pump blood through the body. So these liquids are in very, very narrow tubes, just like the veins inside a tree for the water inside the leaves, whatever. And just by the nature of the liquid in the tube, the liquids are able to climb up the walls of the tube. And this happens in everything. If you're drinking a glass of water, it's happening right now. The problem is that the wider the tube, the harder it is to see. So you've probably never seen it in a glass of water because your curve is super, super, super slight. But the more narrow the tube, like in a thermometer or a graduated cylinder, the more dramatic it is to see a curve. What pops in my head is a volumetric pipette that measures only one volume at a time. Those babies are real thin, so those curves are super dramatic. Those curves are called meniscus curves. Now, what a lot of people don't realize is that these curves are actually three-dimensional. It looks like we have a thumbprint sitting on the surface of the liquid because it's climbing up around the entire circumference of the tube. So reading curves, you've probably been taught this in middle school, but I'm going to remind you, graduated cylinders and other devices have concave curves, meaning that they curve down, just like this one right here. You don't really need to know the difference between concave and convex. You just need to know that if your curve is dipping down, that you read the bottom. And then in your thermometers, you're going to have convex curves, which means they curve up, and you read those from the top. So if you're curving down, you read from the bottom. If you curve up, you read from the top. Best way to read these curves is at eye level. So you would squat down almost so that your chin is at the same level as the tabletop. Don't touch your chin to the table because that's kind of icky. but you're going to look straight on at the curve to figure out the measurement. If you lift the cylinder to you, you're going to wind up jiggling the liquid around, so you're not going to get the most accurate reading. If you read from too high up, you're getting a downward type angle, so you'd be reading like this. And if you're too low, you'd be reading up. You want your eye to be as close to level as possible without touching the tube. Now, this is a picture of test tubes. We don't measure stuff in test tubes. This is just here for the purpose of the diagram. It also doesn't have measurements on it, which is how we are reminded not to measure in it. So recording measurements is probably the new part of this for you. When we start recording measurements, we need to write down all of the digits we know for sure, and we need to write only one additional estimated digit. Now, this sounds kind of silly until you see an example, but I'm giving you the rules first and then some examples. So we're going to write down everything we know for sure and estimate one digit. Here's what that looks like. Here we have a graduated cylinder. It's counting by ones. Each of these dark lines is 1 milliliter. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. They're not writing every single little digit here because it gets to be cluttered. If this were a 4, that would be 5. And if you could imagine a 5 here, it kind of eats up a lot of space. So this one, this graduated cylinder, the bottom of the curve is hitting equally between 8 and 10. And if you can see, there's kind of a little bit of the line underneath here, just reminding you that it's at 9. Some of you may want to just write 9 milliliters, 9 ml. That might have been okay in middle school, but it's not good anymore. We need this to be the digit that we know for sure, 9, plus one estimated digit. So our estimated digit is going to be 0 because this is falling exactly on the line for 9. It is 9.0. It is 9 exactly. This is the digit we know for sure. And this is our estimated digit. Now, everyone's estimated digit is going to be a little bit different. You may look at this. I mean, this is a pretty straightforward example, but if this were in a lab setting, you may say it was 9.0. Your lab partner may say it was 9.1. This 9 is the number that everybody in the room is going to agree on, and this is the number that gives us a little bit of space for human error. Now, the more numbers or the more graduations on this cylinder, the more digits we get back here. But the last one should always be the one that differs from person to person. And everything before that final digit should be something that every scientist in the room can agree on. So here's another example. We are going by tens here, which means that each one of these little lines is 2. So this would be 30, 32, 34, 36, 38, 40. This baby, the bottom of the curve, is sitting on exactly 100, but we're not going to write 100 milliliters because 100 is what everybody in the room knows. You need to give one estimated digit. Because this is falling exactly on the line, your estimated digit is going to be 0. So this is 100.0. In real life, you may see 100.0. I may see 100.1. That's okay. We're still agreeing on this 100, and that is the important part. Okay, this one's a little different. The numbers written here go by 40s. So this big bold line in between 40 and 80 should be 60. 40, 60, 80, 100, 120, 140, 160. If this is going to be 100, like I just counted before, and it's falling exactly on this line, everybody in the room is going to agree it's 100. But we need this estimated digit to say, hey, it's falling exactly on this line. This is 100.0. Are you ready for level 2? I can't get a response from you because I'm doing this in the future. But here we go. Okay, this is a 10 milliliter graduated cylinder. It goes by ones, but it's written by twos. So this is really 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But only every second digit is written to keep it from looking cluttered. So if this is 6 and this is 8, that means that this bolded line in between them needs to be 7. For this to go from 6 to 7, this is going to be 6.0, 6.2, 6.4, 6.6, 6.8, 7.0. Now, everybody in the room should agree that this is 6.6. So everybody should have 6.6 written on their paper. For some people, this may be 6.59. For some people, it's going to be 6.60. For some people, it's going to be 6.61. That's okay, as long as we're all in the same ballpark. These are the numbers we know for sure. This is our estimated digit. Last. I don't know if you noticed, the line just moved here. This one right here is not falling exactly on a line. Should I give you a second to figure it out? Can you do it? I know you can do it. Here we go. This is 1. That's 2, 3, 4, 5, 6. This liquid level is falling in between 5 and 6. So my leading digit is going to have to be 5. There's going to be a 5 right there. Now the question is, it's 5 point what? I am going to say, and I wrote an answer behind here, and I honestly don't remember what I put there. It's kind of embarrassing. This is this is so silly. This is a 5. This is 5.2. This line here is 5.4. So now, instead of my water level being between 5 and 6, now I know it's between 5.4 and 6. It's actually in between 5.4 and 5.6. I'm going to say it's 5.42. Me from the past said 5.43. That's okay. You may have 5.41. Oh, dogs are barking. I think that's my cue to feed them dinner. 5.43. That's where we're at. Everybody in the room should agree that this is at least 5.4, and our last digit is the estimated digit. That's all. That's all it takes to read measurements. Thanks for stopping by. If you need to rewatch, go right ahead. Make sure you filled in your notebook pages, and I will see you tomorrow.